All right, good morning, everyone. We're missing a bunch of people. Okay, we'll figure it out. We'll find out there. So, start with a couple of reminders. So first off, don't forget, exam number 1 is Friday, so 2 days from today. So we'll finish off all the material that we need for today. Tomorrow we'll do a review, do some more group assignments, get some more extra credits. Also this morning, I realized I didn't post the extra credits for the exam, so I did that this morning, so at least you got 2 days to work on it, so not too bad. So that's pretty much it. So the last topic we have to finish is the Doppler effect, not the Doppler effect. All around there. There we go, Doppler effect. So we started talking about this last time, and what we said was that the Doppler effect is the apparent shift in frequency due to motion. So this can happen one of 3 ways, basically. So the first way is that either we have a moving source, third way is that we have a moving observer, or the final way, the third way, is that both are moving. So even though I played this video on Friday, I wasn't sure if everybody could actually hear it since we had technical issues, and that's fine, we'll start over again. So again, here is a guy playing a trumpet, moving in a car. So the first part of the video is his perspective from the car. So he's moving with the car, which means there's no relative motion between the two. So the note that he's going to play will be the note that he hears the entire time. Very annoying note, but that's fine. So now we're going to switch to the roadside, which is now going to be a stationary observer relative to the moving car, which means there's a relative motion between the two. So that's the Doppler effect. So as the car is moving towards them, there's an apparent upward shift in frequency because of the motion. We'll talk about here in a second. And then as it moves away, there's an apparent downward shift in frequency also due to the motion. Okay? So this is what we call the Doppler effect. So Doppler effect is that switch in frequency or pitch due to the fact that there's some sort of motion. Okay? So how does this occur? So let's look at the first case. So let's look at here, we have a moving source. So this is going to be our first case. So this is a moving source. Good. So let's say that the source is actually giving off a frequency f, okay? And then the source is moving, in this case, to the right at a velocity of v sub s, which is velocity of the source. Okay? So at the initial time, which is where the car is here, it gives off a wave pulse, which then has a wavelength. So this is the distance the wave pulse is moving because it's moving at the speed of sound. So again, it's moving in all directions at the speed of sound, even though I drew only one radial vector on here, but they're all moving at the speed of sound in all possible directions. So this is at, say, time is equal to 0. So this is where it is at t is equal to 0. Now, what will happen is the car is going to move forward, and as it moves forward, it still gives off frequencies, which means it still gives off that same wave pulse at this point. But this wave pulse has moved, because it continues to move out at the speed of sound, and it has moved to now where the orange is. Okay? Now the time frame it has taken for this to happen is, since this is the wavelength, the gray here going from this one out to that one, that means it has taken a time of simply the period. So this has happened in the time frame of a period. Meanwhile, the car has moved from this position to this position also in the time frame of a period. So the time lapse from here to here is also in the time frame of the period, which means that here we're seeing the car at t is equal to that of the period. Now, what happens then? Well, for the observer here, what the observer is going to notice is that the frequency, or in this case, the wavelength has changed. So why is that true? So before I come back to here, let me show you a simulation. So here, let's say here is a planet, which is giving off some sort of frequency. Let's call that the Earth. And then that is communicating with this rocket here, which is now in this case stationary. So this is giving off constant frequencies, which are coming off. So each one of these represents a wave crest, which is moving. So this is the wave front. So each one of these is moving away. But this is periodically giving them off, which means that this distance between here is the wavelength. Okay? So what we're seeing in this box here then is the frequency, which is given off, or at least what this guy is actually measuring. So this is measuring the wavelength between the two of these. Okay? So if I look at this distance here versus this distance here, these two have exactly the same. So this is seeing the wavelength, so it's encountering all of these different wave fronts at a rhythmic basis because it's giving off a constant frequency. So this is the wave. Now what happens if I cause this guy to move? So in this case, we're having an observer stationary with a moving source. So in this case, as this guy starts to move closer and closer, as he's moving, he's still giving off these wave fronts. But what's happening then is that the frequency, or at least the wavelength between these two is now changing. Now, as it starts moving away, that wavelength then seems to be bigger as opposed to when it was moving towards him. So let me kind of reset that so you can see a little bit better. So again, as he moves in his direction, since his motion, every time he gives off a wave pulse, that wave pulse is closer to the original wave pulse that came off, which means that what he sees then is a shrunken wave length. Then when it passes him, he sees this one, but now it takes much more time for the second one to come because now it has to travel a further distance, which means he now sees a longer wave length. Now, because of that, as this thing is moving in, because he sees a much shorter wavelength, what he thinks then is because the wavelength is shorter, that then corresponds to a greater frequency. Right, because remember that the velocity has to be equal to the wavelength times the frequency. So as the wavelength goes down, the frequency then has to go up. As opposed when it switches to the other side, the wavelength has now increased, which means the frequency has now decreased. Right? This is the source of the Doppler effect here. The other option is, let's move the observer. So if I move the observer, what will happen in this case is this guy's giving off constant frequency, but again, he's moving, which means he's going to encounter each one of these frequencies at a much quicker rate, which means the wavelength again is going to shrink. As the wavelength again shrinks, frequency then goes up, but again, on the way through, he's now moving away, which means he's moving away from each one of these guys. Let's show that again. So again, here he's moving, he's encountering each one of these wave crests, which means to him, the apparent wavelength is now getting smaller. As he moves past, he's now chasing this one, so it takes much more time for this wavelength to actually catch up with him, which means he sees an elongated wavelength in this case. Or the third case is now they're both moving. So in this case, what's happening is now his motion is causing these wavelengths to get smaller, but he's also encountering them much sooner, which causes even a smaller wavelength than what it would be in that case. And again, as he moves to this side, since this guy's moving away, he's moving in this direction, these wavelengths may never actually catch up to him. So he may never actually hear it. So this is the Doppler effect. Now, one other interesting thing I kind of want to show you here is, let me take off the max speed limit. What happens if I give this guy a tremendous amount of speed? What happens in this case? So what happens here is each time he gives off a wave pulse, he's actually already past the location at which that wave pulse then starts to move out, which then creates this kind of cone effect. So if you notice, every time he gives off a wave pulse, since he's moving faster than the speed at which the sound is moving, it then kind of creates this cone-like shape around him. This is what's called a shockwave. So if anybody's ever watched an air show and you hear them have the sonic boom, what's happening then is the plane is moving faster than the speed of sound, which is actually creating this shockwave. So basically what's happening here is you're creating this effect. Okay. So what's happening here is that the plane is moving faster than what the sound wave itself is actually going to move outward at. Okay. So basically this cone is created by the fact that it gave off a pulse here, then it gave off a pulse here and a pulse here, but each position, it has moved faster than the speed at which this wave is moving outward, which actually creates this cone-like effect around the plane. Now what's interesting about this is the cone is actually an optical effect. You don't actually see this. And the reason for that is the sound comes from the fact that the air molecules next to the plane are moving much faster than the air molecules away from the plane, which means you create this huge pressure difference between the two. That pressure difference of the sonic boom that you hear is the fact that you're ripping the air molecules apart from this created pressure difference which then causes that sonic boom to actually happen. It's the same thing when you take a, like a whip or something and you actually cause it to crack the whip. You hear that cracking sound because you're creating a pressure difference between the tip of the whip versus the air around it. So what's actually happening is with the tip of the whip is moving faster than the speed of sound. So you're ripping the air molecules apart, which is creating that cracking sound. So what's happening here is since the air molecules here have a much different pressure than what they have out here, you get a different index of refraction, which means the light which is coming in scatters off of these particles differently, which is what creates this cone-like shape. Right? So this cone is actually not really a physical thing other than the fact that the pressure here is much different than the pressure here. So this is actually an optical effect of what you're seeing. But this is what we call the shockwave. So the sonic boom comes from the fact that, again, you're moving much faster than the speed of sound. So these are the Doppler effects. So again, what this is happening is this is giving off pulses. Again, this pulse is growing, this pulse is also growing, but again, the distance between this pulse and this pulse is not the wavelength at which it should be, but it's a shrunken wavelength due to the fact that the car itself, in this case, or whatever the source is moving. So we want to know, what then is the apparent frequency? So what do we actually hear in this case? So from here, what we can see then is that the apparent wavelength then is going to be equal to what? The velocity of the sound times then the period. So that's actually the actual wavelength. So this is the actual wavelength. Minus then the speed of the source times the period. So basically here, so all I'm doing here is I'm taking this distance of the wavelength, subtracting off then this distance, which is then giving me, Now the period is the same, so this is going to be equal to then the speed of sound minus then the speed of the source, all then times the period. Now what we also know is that the period is equal to 1 over the frequency, and then the apparent frequency is going to be equal to the speed of sound divided by the apparent frequency. So putting these things together, let me go back a slide. So we now have that this is equal to the speed of sound divided by the apparent frequency. And this guy's going to be equal to the speed of sound minus the speed of the source, divided by the frequency. Write that on here. So I get the speed of sound divided by the apparent frequency is then equal to the speed of sound minus the speed of the source divided by the actual frequency. So let's cross multiply. So ultimately what this thing says then is that the apparent frequency is equal to the actual frequency times the speed of sound divided by the speed of sound minus the speed of the source. And this is true for when the source is moving toward the observer. Now, if I go back, what would be different than if the guy was standing on this side? What would be different is instead of having a minus sign here, I'm going to have a plus sign. It's basically the only difference. So what happened in this case then is I have this distance on the wavelength, but now I want this total distance, so it's going to be added then to the distance of the car, which means that when the source is moving away, I get the apparent frequency that is the actual frequency times the speed of sound divided by the speed of sound plus the speed of the source. This is when it's moving away. Okay? Now, case number 2, when the observer is moving. So when the observer is moving, we have a source which is giving out a frequency which is fixed. So this is fixed in location. So this is going to give out one wave pulse, give out a second wave pulse, so that this distance here is going to be the wavelength. So now I'm going to have an observer here moving now, say, toward the source with the velocity of the observer. So what's happening in this case? Well, in this case, we have what? The speed of sound is moving outward in this direction. Speed of sound. While the observer then is moving towards the source. So what will happen then is as he's moving, he's going to encounter this wave, but but he's going to keep moving here, which means he's going to encounter this wave sooner than what he should have if he was stationary, right? Which is causing the wavelength to actually shrink in this case. Now, him, we can then say, well, what's happening here is not the fact that the wavelength is changing, but it's also messed up because of the fact that he's moving, which means his relative velocity. Now, I know in my 205 we didn't really talk about relative velocity, but relative velocity is basically, if you think about the fact that if you're driving in a car and you're driving down the road, and let's say you take an apple while you're driving in a car and you throw it at a mailbox. Did this once as a kid, it was fun. Watch the mailbox crumble, it was just amazing. But anyway, so what happens? So if you're driving in a car, let's say you're doing, I don't know, 45 miles an hour, you take the apple and you throw it out the window and you throw it at another 50 miles an hour, how fast is the apple actually moving? So by the time that apple hits the mailbox, assuming it's in a vacuum so there's no air resistance, right? How fast is the apple moving? 95 miles per hour, right? Because the car is moving in this direction at 45 miles an hour. You are also moving at, and then you throw the apple at what, 50 miles per hour. So the total velocity at which that apple is moving relative to the mailbox is the sum total of the two. That's what's called relative velocity. So relative velocity then is having the fact that that's what, if you're moving in an opposite direction of something, what you see is the sum of the two velocities together. Meaning that when you're driving your car on the Lloyd, you're doing 80 in this direction because everybody does 80 in the Lloyd. Another car is driving in this direction on the Lloyd doing 80 miles an hour. So if you say you are stationary, how fast is the other car moving? 160 miles an hour, right? Relative to your position. But if you're driving next to the car, you're doing 80, they're doing 75, slow bastard, better get out of my way, right? How fast are you going relative to that car? 5 miles per hour, right? So if you say that the other car is stationary, you're only going 5 miles an hour faster than a car, so the relative velocity between you and that car is 5 miles an hour. Right? So that's what's going on here. What's going on here is the speed of sound is going this direction, you're moving in this direction, which means if you pretend you're stationary, how fast do you see the speed of sound going? At the speed of sound plus your velocity. It's going much faster in that case. So for this case, the apparent frequency here then is going to be equal to the speed of sound plus then the speed of the observer. Pardon me. So this is your relative velocity, right? All divided by then the wavelength. If I got that quantity right. Yeah. Good. Now, the wavelength though should be equal to what? The speed of sound divided by the actual frequency. Because here what we're saying is that this wavelength stays the same, but what's happening then is that your velocity is actually changing. So this is going to be rewritten then as the actual frequency times the speed of sound plus the speed of the observer divided by then, the speed of sound. Speed of the observer, good. So this is the actual frequency times the speed of sound plus the speed of the observer, all divided by the speed of sound. And again, this is true when the observer is moving toward the source. Well, what happens if he moves away from the source? Color I haven't used it. Use gray. Well, if he's moving away from the source, the only thing that's going to happen now is since he's moving this way, the speed of sound is trying to catch up to him. So it seems like the speed of sound is moving slower than what it should actually be moving. So the only difference here is this becomes a negative sign. So when it's moving away, we have the apparent frequency that is equal to the actual frequency times the speed of the sound minus the speed of the observer divided by the speed of sound. So this is when it's moving away. Okay. So what we call the Doppler effect is actually both of these two effects put together. So the actual Doppler effect is these two things simultaneously. So here this says that the apparent frequency is equal to the actual frequency times the speed of sound, speed of the observer divided by speed of sound, speed of source. So this is going to be plus minus or minus plus. The green here corresponds to when it's moving toward. The blue corresponds then when it's moving away. Now, here we have to take this a little bit with a grain of salt in the fact that we have to look at what each one of the two objects are doing relative to the other one. Right? Which means that, let's say I have two observers which are moving. You're being chased by a cop car. Because you're doing 80 on a Lloyd you're not supposed to be, so they may actually pull you over for once. So in that case, you have this cop car chasing you. So in this case, the cop car, which is the source, is coming towards you. In that case, you would say the source is moving toward, so that goes with the negative sign. You, as the observer, are moving away from the police car because you don't notice they're there because you got your music cranked up too loud. You don't actually hear it, right? Which means you are simultaneously moving away from the police car, which means that would correspond then to a negative sign. So when you're trying to determine the signs you use for each one of these, you have to look at how these objects are moving relative to each other. So they would only both be toward if they're physically both moving towards each other. So if I have two objects which are both moving towards each other, for example, you're moving this way and the ambulance is going in this direction, that way the ambulance will be moving towards you, you are simultaneously moving towards the ambulance, so you both will go toward. Police car is chasing you. In that case, police car is moving towards you. You're moving away from the police car, so you'd have to look at it that way. So when you're simultaneously trying to determine these signs, you have to look at how these guys are moving relative to each other. So you have to look at them independently, what they're doing relative to the other object. So that's how we determine the signs. So this is what we call the Doppler effect. So this is actually both of these two things simultaneously. So the Doppler effect itself takes into account that the observer and the source can both simultaneously be moving. If one of them is stationary, you just call that guy equal to 0. So if I have a moving observer with a stationary source, this velocity is 0, this one is not. If the source is moving and the observer is stationary, this one is 0, this one is not. So let's do a couple examples. Let's see how this works. So the first one, there we go. So the first one has to do with a cop car chasing you. So this is a police car moving at 80 meters per second, chasing a speeding car moving at 45 meters per second in the same direction as the police car. If the siren of the police car is 800 hertz, so this is the unshifted frequency, what is the apparent frequency heard by the car? So let's draw this. So here's my police car, moving in this direction with the police car. Here is my observer, my speeding car, moving in this direction with the car. What I know is that this one is 80 meters per second. This one is 45 meters per second. So this one is giving off a frequency. That frequency was, what, 800 hertz, if I remember correctly. So this is my police car giving off red lights. So we want to know then, what is the apparent frequency heard by the speeding car? So what is F prime? What is that apparent frequency? So for here, since I didn't tell you a temperature, let's go ahead and take that the speed of sound in air is 343 meters per second. So we need to know that piece of information. So we now know this is equal to the actual frequency times the speed of sound, speed of the observer, divided by speed of sound, speed of the source. So again, when we look at these signs, we then have to ask, what is the observer doing relative to the source? Well, in this case, the observer is the car. The car is the one which is actually hearing the frequency of the police car. So in this case, we can see that he's trying to move away from the police car. So since he's moving away, this then corresponds to a negative sign. Simultaneously, the police car is trying to move towards the source, or so towards the observer. Since he's moving toward, this is also corresponding to a negative sign. So this is then equal to the speed of sound minus the speed of the car divided by the speed of sound minus the speed of the police car is equal to the apparent frequency. So let's look at our numbers. So this is then going to be equal to 800 hertz times 343 minus 45 divided by 343 minus 80. So my apparent frequency then should be greater than 800, since it should be shifted upward. In this case, it works out to be about 904.5 hertz. This is my apparent frequency. Okay? What's up, Dylan? Right, so in that case, if the police car was moving, but the car was not, the only difference is that 45 would be a 0. So in that case, then, that's an interesting question. I don't think so. And the reason for that is because here we're dealing with subtraction. So the ratio would change. Right, so if I tried to say he was 0 and he was 45, then that changes the ratio of 343 minus 45 divided by 343 minus 80. So that's now 345 divided by 345 minus 45, which is not the same ratio. Okay. So in this case, I'm taking the velocities relative to the ground, not the velocity relative to, say, the car itself. Because again, that's going to cause a slightly different ratio, which would cause a slightly different answer here. Yeah. So good question. Yeah. So in this case, I'm always looking at the speed relative to the ground. That's helpful. So let's do one more. So this example says that we have a platform attached to a truck which carries 2 speakers, one at the front end of the platform and one at the back end of the platform. Each one of these speakers gives off the same constant frequency of 440 hertz. So then it says if a person is standing midway between the 2 speakers, here's a beat frequency of 10 hertz. What is the speed of the moving truck? Okay, so this is our first example of a beat frequency. So let's talk about this. So let's say here's my truck, my beautiful truck, moving in this direction with a velocity v of truck. Okay. Attached to this is the platform. Here's my platform. I have one speaker on this side giving off frequency of F. I have another on this giving off frequency of F. Wheels on here. Here we go. And then midway between the two, I have a person standing here. And then what are they going to hear? So what'll happen then is what? Sound from this guy is going to travel to him, but this one is going to be upshifted, right? So let's call this frequency from the right, and what we know is that this frequency here should be greater than the actual frequency of F. And the reason for that is what? This speaker is moving towards the observer, which means this should be upward shifted, right? Simultaneously, this wave, which is coming to him from this side, let's call that frequency left, this one is going to be downshifted because this speaker is simultaneously moving away from this guy. Right? So this guy's stationary, the truck is moving in this direction, which means this one is moving towards, so this one has an upward shift. This one is moving away, which means it's downshifted. So what we know is that this guy is going to be less than the original frequency. Now what it goes on to tell us is that the beat frequency, so we talked about this on Friday, the beat frequency, which is equal to the difference in the frequencies, so in this case this is going to be the difference between the left and the right frequencies, is equal to 10 hertz. So remember, beat frequency is simply the difference between the frequencies. So this one is shifted up, this one is shifted down, and the difference between that upshift and the downshift is equal to the beat frequency, which is equal to 10 hertz. From this, we now want to know how fast is the truck moving. Okay? And again, we know our frequency is 440 hertz. Good. So for each one of these guys, let's use the Doppler effect. So this is going to be equal to the actual frequency times then the speed of sound, speed of the observer divided by speed of sound, speed of the source, which in this case is going to be that of the truck, minus the frequency times the speed of sound, speed of the observer, divided by the speed of sound, speed of the truck, because the truck in this case is the source. Now, for both of these, the observer is simply stationary, so he's not moving. So we can go ahead and call this guy 0. So I'm not going to worry about the signs on him. So this one is 0. Now, again, for each one of these, what we know is that the right one is moving toward. And remember, toward corresponds to a negative sign when it comes to the denominator. So this is now a negative. This one is moving away. So he's moving away from him, which corresponds to then a positive sign. Good. Now they both have a frequency, so let's factor that out. So this is going to be the same thing then as the frequency times the speed of sound times 1 over the speed of sound minus the speed of the truck minus 1 over the speed of sound plus the speed of the truck. So that's equal to our beats frequency. Is okay? From here, it's easiest to find the common denominator. Common denominator is simply this guy times this guy. So let's go ahead and do that. So this tells me that my beat frequency is equal to the actual frequency times the speed of sound times then the speed of sound plus the speed of the truck minus the speed of sound minus the speed of the truck, all divided by the product of those two, which is the speed of sound squared minus the speed of the truck squared. Okay? Now here, oops, sorry, should be a plus sign. So here what we can see then is that what? Speed of sound gets added together. Actually, no. And they're right the first time. So this is the negative, but this becomes a positive because I have a minus of a minus, which gives me a positive. Good. Sorry about that. So the speed of sounds here are going to cancel. Good, go away. Thank you. But the speed of the truck, I now have 2 of those. So if I put everything together, so this thing becomes twice the speed of the truck times the frequency times the speed of sound, all divided by the speed of sound squared minus the speed of the truck. Okay? So finally, we're going to multiply this guy over here, divide this guy over here. So I get that the speed of the sound squared minus the speed of the truck squared is equal to twice the frequency divided by the beat frequency times then the speed of sound times the speed of the truck. Finally, what I notice is I have a speed of the truck squared here, a regular speed of the truck here, and a constant term here, which means we're going to have to solve a quadratic. So let's make this thing actually look like a quadratic. So I'm going to go ahead and add this guy over here, subtract this guy over here, to finally get 0 is equal to the speed of truck squared plus twice the frequency divided by the beat frequency times the speed of sound times the speed of the truck minus the speed of sound squared. Okay? So this is just a quadratic. So whatever shows up in front of VT squared is A. So A is just equal to 1. Whatever shows up in front of VT is B here. So twice the frequency divided by the beat frequency times the speed of sound is simply equal to the speed of the, or equal to B. And then whatever this thing is C. So that's our C. So let's plug in our numbers. What we finally get then is that the speed of the truck, and here again I'm using the speed of sound in air, is 343 meters per second. Works out to be 3.9 meters per second. This is the speed of the truck. Is okay? Not too bad. So this is the Doppler effect. So again, Doppler effect is the apparent shift in frequency due to motion. If an observer is moving towards a source or a source is moving towards an observer, there should be an upward shift. So the frequency should be higher in that case versus if it was stationary. If it's moving away, either one, if the observer is moving away or the source is moving away, it should be shifted downward, so it should always be lower than the actual frequency. Again, a beat is simply the difference between 2 frequencies. This is a beat. Okay? Nathaniel. Sure. I forget sometimes I write too fast. You're good? Okay. So that's it. We're done. Life is good. So that brings us to group assignments. If I can find it. There we go. So let's do. So I have two for you. So I'm going to bring up one at a time. Once I find them. Here's the first one. So the first one says that the Doppler effect is used in ultrasonic waves as a, so the original frequency which comes out is 2.25 gigahertz, times 10 to the 6, so it's a megahertz, sorry, is used to monitor the heartbeat of a fetus. So it says the maximum heartbeat, so the maximum beat frequency that it observes is 260 hertz, okay? So it says, assuming that the speed of sound in tissue is 1,540 meters per second, determine the velocity of the surface of the beating heart. And we'll talk about this in just a second. And then part B then says, so if the amplitude of the heart's oscillation is 0.2 centimeters, what is the angular frequency? Okay. Now, this problem is kind of tricky, which is kind of tricky for the same reason that sonar is kind of tricky, in the fact that what's happening here is the heart is simultaneously acting as the source and as the observer. All right. So what do I mean by that? So what I mean is, say the heart is oscillating like this. Okay? The original wave comes in, which means that the original wave which comes in is Doppler shifted by the fact that the heart is acting as the observer. Okay? So there's an automatic Doppler effect and Doppler shift due to the motion of the heart. But the heart is going to bounce off that wave and then cause that wave to start moving back to the ultrasound, which means that now the heart has shifted from the observer to now the source. So the heart is now simultaneously the source of the reflected wave. What's happening here then is that the ultrasound system itself is taking a beat frequency between the original wave which was going out, which is 2.25 megahertz, versus the secondary Doppler shifted wave. So what happens is as the heart is moving, it sees a Doppler shifted wave coming in, it reflects that wave, but that wave then is a reflection of the Doppler shifted wave, which is now Doppler shifted again, due to the fact that it now is a moving source. So the point of all this is that the heart is simultaneously acting as two things. It's acting as the source and the observer. Each one of those two is Doppler shifting the wave. Okay? So let me kind of draw what I'm talking about here. Since even through Vanya's mask, I can see she looks confused. Okay, everybody's okay? So here is the original, which is sending out the wave. So here's the wave. The wave has the original frequency. Our heart is out here. I'm gonna draw that as my heart. Here's my heart, okay? So my heart is harmonically oscillating back and forth for the wall, okay? So let's say, so here we have to make a choice. We have to assume by the time the wave comes in, is the heart moving toward or is it moving away? It doesn't matter as long as I'm consistent. Whichever I choose doesn't really matter. Okay? So who should I pick? So Grant, which way you want it to be moving? You want it to be moving toward or away? Toward, great, okay. So this is my velocity of the heart, right? So what's gonna happen is, since the heart is moving toward, that means that the wave which is actually encountering then the heart is seen at an apparent frequency of f prime. Okay? But that heart then is going to reflect the wave. That reflected wave then is gonna come back this way. But now what's happening is the heart moving is reflecting the wave, which means the wave then that's reflected backward is shifted a secondary amount. Let's call that f double prime. So what's happening is the heart is reflecting the wave, but it's reflecting the wave at a frequency of f prime, not the original frequency of f. because the heart is moving, right? So for the orange one here, the heart is acting as the source, or sorry, as the observer. But as the green one, it's acting as the source. The beat frequency then, our change in frequency, which is then the beat frequency, in this case is going to be equal to the second shifted Doppler minus the original frequency. So that's this guy. So this is what you're working with in this problem. Now this is the same thing which happens with sonar, right? So if you were, say, in a submarine that's moving towards another submarine which is moving, and you send out a sonar pulse to find out where that submarine is, that secondary submarine acts again as the source and the observer simultaneously. So it is the observer to that original wave which is coming in, but that wave gets reflected back to you. So you're measuring that beat frequency, but due to the motion of it and the fact that it's reflecting it, it acts then simultaneously as the source. So this problem could be directly related to sonar as well. Okay? So this happens in sonar as well. So we have about 20 minutes, or no, about 9 minutes left, sorry. So I'll let you guys kind of start working on this one. I'll bring up the next one tomorrow after we do the review for Friday's exam. So basically you have all the pieces here. So now all you have to do is apply Doppler effect twice. Make sure you apply it first onto this one. Use the fact that this one is reflecting that one, not to the original one. So, Corey.
Can you go back to the problem?
Oh, sure. Just want to see the fetus again? Oh, so you have to look at what they're doing to your initial. So when it comes to the heart here, that's why I was saying we have to choose what the heart is doing relative to the source. So what Grant had chose was that the heart was moving forward. So here, it's acting as an observer, which is moving through. So we would then go back to our. So now we're saying that we have an observer. So we have a stationary source, moving observer that's moving. So which one of our signs are positive or negative? So the velocity increasing or decreasing? Increasing, good. So you use the top. So that means then, if you're going to write that down front, we would just use this, as 0. So now I have to look at the part again as now the source. Now I have the source. It's still moving forward, so it's still moving in the same direction. So now this part is now the source. It is now moving toward the cells. Or sorry, toward the cells. Correct. Is now the source. Yes. And now it's moving toward it. So it's toward corresponds to positive or negative. Oh.
Okay, so if it's towards
because the negative, I mean, right? So think about the denominator is smaller than increase. Where it's opposite. So it makes the number bigger, or numerator add in, and it'll make that numerator bigger. But the denominator is also. Makes sense? So what that one is reflecting, though, is now prime, not the original. So now you got to face it. What's up? Right, so that becomes the Okay, so in the first case, it's acting as the observer, so there is no source motion. Well, that's for the next one. So for F double prime, right. So for F prime, what's happening is the heart is acting as the observer and the source is stationary.
Big G.
Well, it's not. So it's only the heart. So for F prime, what's happening is the heart is moving as the observer, but the source itself is stationary. Then with the reflected wave is now sourced by the heart, which is moving, but now the observer, which is the original ultrasound machine, is still stationary. So now the observer in that case is. Well, that's what we're trying to find.
Which way? So you say electric wave.
Yes. I'm sorry. Well, yeah, we have to be consistent with whatever we showed you.
Okay.
Yeah. So it was moving toward as the observer and so moving toward as. Because again, we're moving in the opposite direction. Correct. Yeah, so at double prime minus. So is equal to this, we'll see the ground, minus in 2.25. Yes. So you're almost. So this is only when it was shifted to it being the observer. So this is only F prime, not F double. So if I have double prime, you can still be the fact that now it's shifted to the source. So this is actually only F prime in this part of the exercise.
So now I need to look at
Correct. So this is all. So this is all just F prime. So we just have that double prime and then F prime. Now times the fact that it's sound, divided by the speed of sound. So basically the sound is basic. And now since this height is moving away, of course our negative.
well, I was thinking probably
Oh, okay. So in that case, then yes.
that'll be negative.
So would be a plus. Which is fine. The only difference then, when I do it that way, is that that's what happens to go first minus this. Otherwise, you're going to get a negative. So that's basically so now you need to basically multiply this push down.
And then once I get down, then you just solve.
And that's all equal to 250. Once it's directed. So now it's the moving. No, it's still moving in the same direction.
So it's still.
Yes, that's right. It's still going to right. Now it's doing the two things at the same time. Oh. Yes, correct. So that's F double prime minus F. Yeah, I mean, you can do it that way, but then you still need to write F double prime. Sure. So this becomes here, that should be an line now. Where that it's F double prime, now put that here.
B sound.
Yep, this is where so just make that here. And then it should be double prime. This time you're doing this after the 260. Yep, Yeah. Yep, and just all. So I think we are technically out of time. So we'll call that a day. You guys can keep working on these. So one thing I'll mention this tomorrow, but I think what I'm going to do with the group assignments is instead of having you guys pen and paper, I'm just going to have you take pictures of them and then upload them online. So I'll get all that set up to be ready for tomorrow. So you can start doing that tomorrow. But I guess I'll tell you that tomorrow. Yes. Yeah. So here the BD sound we cancel the rows. So now you just want to get this guy on the track. That guy and that correct. So yeah, so it's the only thing you need to do that frequency. Correct. Yeah, so you don't have to have it. However you like it. Good. Right, so now what's happening here is now the observer station is 0. That's going to be oh, that's what you're trying to follow. So just leave it at 2. So I'm just giving you the answer so you know what yeah, exactly. So yeah, so you have a V part here. This one should be 0. And should be V part there. Because now what's happening is the reflected wave was acting as the observer is the ultrasound system itself. Okay? And that guy's not moving, it's just sitting there on the net. Okay? So in the first case, it's the source which is moving, not moving because it's this. And then the reflected wave, now he becomes the observer when he was originally the source. And he's still on. Make sense? Yeah. All right. It's a little bit tricky, but once you kind of understand how to do it, then yeah, it's not too bad to have to talk. What's up, Corey?
Forget my brain wasn't on the show.
Oh, I know. I forgot mine this morning.